quadratic equation, our red line. And all of these tangents are our derivatives at particular points on that line. But as we were talking about, for a quadratic, we get a straight line as the derivative, but that's not always the case. So we'll go through some other examples. So we looked a bit at this. Previously, we used our definition of a derivative to find out what the numeric derivative was at a particular point. But what if we want a general solution? So general being that we're not saying, okay, what's happening at x equals 1. We want to know, for any value of x, what is the derivative of my function? So we can do the same process. We start with our definition of a derivative up here. We've got our function. Again, we're going to look at y equals x squared. And then we're going to use that definition to give us a form of our derivative for any x. So we substitute our x in here. This is essentially our x plus h squared, because we've got y is equal to x squared. And then we can start rearranging. So we substitute our function in, we rearrange until we get something like this, where we've got our derivative is equal to the limit as h tends towards 0 of 2x plus h. So here now we can say, okay, well, as h tends towards 0, we get our solution, as it were, our general solution, that the derivative of y with respect to x is equal to 2x. Okay. So now you've got this. X equals 1 is a special case. You can substitute in x equal to 1, and that gives you the value of your derivative at that point. But this equation gives you your general solution. And as you can see, it's linear. So we've got our derivative is equal to 2x. We're not going to differentiate from this is called differentiating from first principles. We're not going to do that for everything, but it's helpful to think about some of the steps and how you apply that definition to get your derivative in the first place. Okay. So, going back to our example, here's our equation, y is equal to x squared, and we've just found the general solution of our derivative is equal to 2x. Okay. So we've got a quadratic equation, and our derivative is a straight line. So essentially, the derivative of a function is just another function. There's some good news, some bad news, and some good news with doing this. So, as I said, you can find the derivatives using differentiation from first principles. So going back to that definition of a derivative, and then working through, substituting in your function, rearranging, and then tending h to 0 and seeing what you get. You don't have to. It can get quite awkward. And again, some previous mathematicians have done a bunch of work on this, which you can leverage for your own analyses. So chances are you're never going to be differentiating from first principles, but it's good to understand where it comes from. So essentially, we're going to go through some key examples of derivatives and ways that you can calculate derivatives if you've got slightly more complex equations. So, here's some examples, or rules. Again, you will be getting these slides, so do not feel that you have to memorize all of this right now, unless you really want to. I mean, yeah, whatever relaxes you. So here we've got some rules. Firstly, if you are differentiating a constant, then your derivative, your general solution of that derivative is 0. And if you think about the graph of that, so here we're saying y is equal to c, so we've got y is a flat horizontal line. That's not really changing with respect to x. So our dy by dx is equal to 0. Okay. We've got the kind of general case of x to the power n. So we just looked at x squared, and we found that the derivative was 2x. The general case of that is if you've got y is equal to x to the n, then the derivative is nx to the n minus 1. So you can see, if we were thinking about n equals 2, we'd have 2x to the 2 minus 1, just 1. Okay. This next rule is why mathematicians really like e. So here we've got y is equal to e to the power ax plus b. If we differentiate that, the only thing that changes is we get an a down in front, but otherwise it looks pretty similar. So if we had a is equal to 1, when we differentiate it, we get the same thing. It's quite handy. It's a nice property. It gets used a lot for that reason. And then there's some trig derivatives. So differential of sine of ax plus b is equal to a cos ax plus b, and so on. And then finally, let's say you're differentiating log of base e. So we're thinking about e to the power of this term, log of base e. If we differentiate that, we get this fraction a over ax plus b. So again, if b was equal to 0 and a was 1, when we differentiate this, log e to the x, we get 1 over x. Again, it's quite nice for log base e. So we've got a few rules, or rather, not so much rules, but someone's already worked out these from first principles, so we don't need to do it again. If we know these, and we've got some other kind of rules or equations for working with slightly more complex differentials, then we can start building up when we calculate our derivatives. Not everything is differentiable, but for the purpose of this lecture, we're only going to look at things that are. We can come back to that at another time. But just to give you a limit, saying that not everything is differentiable. It has to reach certain conditions. And one example is, what if we've got y is equal to the modulus of x? And we're thinking about what's the derivative when x is equal to 0? It doesn't really quite make sense. Okay. So let's think about some rules or how we build up differentiating functions of different kind of formats. So for an example, if we've got y of x is y1 of x, so one function of x, plus or minus y2 of x, it's the same kind of properties in our derivative. So when we differentiate, dy by dx is equal to dy1 by dx plus or minus dy2 by dx. So if we've got two functions added together or subtracted, when we differentiate them, we can essentially treat them independently and just add or subtract them afterwards. Here's an example. So we've got y is equal to x minus x squared plus e to the 2x. So we've got three functions, but they're only added or subtracted. So we can differentiate them independently and then add or subtract them. So x, when we differentiate it, becomes 1. X squared goes to 2x. We've got a minus sign there. And e to the 2x, we bring the 2 down. We've got e to the 2x. Okay. So sums and subtractions are nice and easy from that perspective. Another nice one is if we've got a constant multiple. So here we've got z of x, z is a function of x, is equal to k, where k is just a constant, just a number. And then we've got this y of x, another function. When we differentiate, we just get essentially differentials like this, but multiplied by k. And you could work this out. So if you had a 2 here and you were differentiating 2x squared, you get 2 times 2x is your derivative. Same thing here. So here we've got y is equal to 10 e to the 2x. we can rewrite that, where we just think about 10 as our constant multiple. We differentiate our e to the 2x, where we just pull the 2 down in front, and we've got our derivative as 20 e to the 2x. Okay, so those are some of the nice things that you can do with derivatives. Sums or subtractions, and then constant multiples. It gets slightly trickier when you've got things multiplied together. So let's say you've got y of x is equal to one function times another. Then we've got a lovely rule for this, called product rule, where we've got dy by dx is equal to u dv by dx plus v du by dx. Again, you don't need to work that out from first principles. This is a rule that we can rely on. If you're interested, you can have a look at the proof, but we won't get into it in this course. So let's say we've got something like this, already slightly more complex in terms of an equation. But here we've got our function x squared, and we've got another function, e to the minus x. So, in this case, u is x squared, v is e to the minus x. We differentiate these. So x squared goes to 2x, dv by dx goes to minus e to the minus x. So pulling that minus down. And then we can put these into our product rule. So we put them together, and we can rearrange just to tidy things up. So if we've got a product of two functions and we want to differentiate it, we've got product rule that we can use. As you can imagine, if we've got a product rule, we might have kind of the inverse or something for quotients. So where we've got one function divided by another. In this case, we've got a slightly different formula that we can use. We can think about it as a special case of product rule, but it's the same set of steps when we try and apply it. So if we use the same kind of equation that we had before, x squared times e to the minus x, because of our rules of exponentials, that's the same as saying x squared divided by e to the x. So now our u is x squared, but our v is e to the x. We differentiate those, and then we put them into our quotient rule and rearrange and get the same answer. Okay. So products and quotients are a bit trickier, but we've got rules to deal with them. And it might be that you have to use them a couple of times, but not in this course. Another useful thing, and we'll come across this quite a lot, is where your function is a function of something else. So, what do I mean by that? Here we could have y of x is actually y of u, where u is a function of x. This looks horrible, but we've got chain rule to use when we're working with this. So dy by dx is equal to dy by du times du by dx. So thinking about functions within functions. Let's look at an example. So here we've got y is equal to e to the x cubed. So we could write it as y is e to the u, that's one of our functions, and u is x cubed. These are much nicer to work with. We're pretty happy with these now. So we can differentiate those. dy by du is just e to the u again. See that we're differentiating with respect to u here, not x. And then over here, du by dx of x cubed is 3x squared. So n times x to the power n minus 1. That's where it's coming from. Now we've got this, we can put it together. So we've got e to the u times 3x squared. We substitute u back in, e to over here, x cubed, and put it all together. So we get a solution for a slightly more complex equation there. Okay. If we wanted to do another quick example, so here we've got log base e of x cubed plus x. So we define our first function as log base e of u. Our second function is u equal to x cubed plus x. Now they're a lot nicer to work with. We can differentiate log base e to the u. That's 1 over u. And we can differentiate this whole term. Again, we've got a sum here as well, so we're actually adding that layer on as well. And once we've differentiated them, we can put them all together, use our chain rule, and get our derivative, our general form. Okay. So again, you get the slides. You don't have to memorize all of these rules straight away, but we will be using them on and off through different bits of the course. So, we need to remember that when we differentiate, we are differentiating in a general form, I should say. We are essentially getting another function. So if we differentiate our x squared, we get our y equals 2x, which is another function. If we think about what's actually happening and how these two relate to each other, if we think about the gradient here, so if you imagine drawing a straight line that moves around, so we're thinking about how the tangent moves around this quadratic curve. If we looked here, we've got a negative gradient, right? We're going down. So we're going down here, and we move the tangent round, tangent being the line that only touches at one point. And that's still negative until we reach this point where it's flat. So the gradient of the line, the tangent here at 0, is flat, so it's 0. And then on the other side of this, we've got a positive gradient, if we think about how that tangent's going round. So what's this showing in the derivative is how the gradient of that tangent line is changing. So this point at 0, that's where we've got this flat line, where we're going from a decreasing or negative gradient changing to a positive gradient. So going from negative derivative to 0 to positive derivative. This is really useful to think about when we want to think about maxima and minima. So if, again, this was an optimization problem and we wanted to find the minimum value, where does that occur? We're looking for that minimum point. It's quite handy to know that that minimum point happens when this derivative, another function, is 0. Because then we can start solving equations set to 0, which is something that we've seen before. So, if we want to find the maxima or minima, or even what we call an inflection point, so where a curve may pause, we want to consider where is the derivative equal to 0? Where have we got a flat line? Nothing's changing. This sort of equation is something that we come across a lot because these points where nothing's changing are also quite interesting for differential equations describing populations or kind of epidemiological systems. This is an interesting point because it might give us an equilibria, but we'll come back to that later. So, it's useful to know that at the maximum, the minimum, or an inflection point, our tangent at that point has 0 gradient. Its derivative is 0. We can't say that that's going to be what we call a global maximum or a global minimum. All we can say is at that point, we're changing direction in terms of the gradient of our tangent. So all we can say here is we know that we're going from an increasing function to a decreasing function. We don't necessarily know that this is the maximum value that this function will ever reach. And as you can see, it keeps increasing over here. But what we can say is this is a change point. We've got a local maximum or a local minimum. That's what we call it. Okay. So, yeah, it comes from thinking about this derivative either side. We thought about how the tangent or the gradient of the tangent might change. Again, increasing, we get to a flat point, 0 gradient, and then decreasing, same from here. So we can get our local maximum or local minimum from that. And we can use that to get an understanding of what our function looks like. So not only are we understanding the function based on the equation of itself, so let's say we've got this equation here, y is equal to 2 plus 3x squared minus 3x cubed. Okay, this is a sum of a bunch of functions that we can differentiate. Sorry, go on.
Just to go back, I wanted to understand the context of local and maximum.
Oh, yeah.
Yeah. Like, in this case, when you say local, or in this case, when you say local maximum or local minimum, I just wanted you to repeat what does it really mean in the context of, for example, if this was an observation you are seeing. So what is your local maximum or local minimum?
Okay. Let's say that we're talking about something like the lynx population that you saw earlier. So with your lynx population, we've got an oscillating time series, right? We've got some sort of seasonality going on. This might be useful if you had a nice equation for that oscillation. What you might be interested in is saying, okay, when are we going to get peak numbers of lynx each year? So you can use the derivative set to 0 and solving that equation to give you an idea of when are we going to get a peak in the number of lynx and when are we going to get the minimum number of lynx in a year. Could be the same for an infection if we've got a seasonal infection where it's affected by temperature or rainfall each year. We might want to know when the key peak incidence is so we can think about healthcare provision accordingly. That's where we might have something like this. It does assume that we've got a lovely equation describing that behaviour, which we might do, but it's not always the case. So that's where we've got a local maximum because it's the peak for that year. But if we look at the entire time series, there might be one year where it's a bit higher or one year where it's a bit lower, but we just want to know the timing of that peak per year. So we might want to know that in January we get the highest number of lynx. But maybe 2023 we had a larger population than 2022. Cool. Yes, that's where we were. Okay, so we've got this equation. It's a little bit complex. If someone asked us to sketch it so we get an idea of how it's working, we can look at this and say, okay, well, it's complex, but it's made up of functions I understand. And they're just added together. So we can say it's 2 plus 3x squared minus x cubed. I keep making a mistake. If we think about the derivative for that, well, if we differentiate a constant, it's 0. Yes. And then we've got differentiating our 3x squared. So this is a constant multiplier of x squared. And we get, thank you very much. And then finally, we've got minus x cubed. So minus x to the power 3. We get perfect. So each of these individual things we can differentiate, and just because they're added or subtracted together, we can put them together in our derivative. So we can calculate our derivative, and we might rearrange to make it a bit simpler. Oh, look, it's a quadratic. And we factorized it, and now we know what the roots are. So we've got a root where x equals 0, and we've got a root where x equals 2. So if we think about what our derivative looks like, it's a quadratic. It crosses the x-axis at 0 and 2. There's no constant, so it crosses the y-axis at 0 as well. And it's got a negative in front of the x squared, so we know it's an unhappy graph. So we've already got a good idea of what the derivative looks like. And the derivative is telling us how our equation that we're interested in is changing. So here we know that it's in what we've got going on. We might be interested in where it's 0. So where is the 0 derivative? We know that means a change point. So we've got 2 change points. So we already know that at some point we're going to have either a flat line there or a flat line there. We know that we've got a change point going on with this. If we look over here and think about the gradient, so here we've got the gradient of our tangent line, it's negative. That's what we've got going on here. We've got our change points at 0 there. And then it starts growing. So we've got an increasing function in our derivative until we reach our change point. Things are at 0 again. And then we've got negative again. So that's over here. So we can use the derivative, which is often a bit simpler than our original equation, to get an idea of what's going on with our equation. We can use the derivative to understand our original equation. Okay. So we had a look at differentiating a few things, a few basic rules. We went through some examples, and then we went through how you can put them together. So either you've got sums of functions that you can differentiate to be sums of derivatives. You might have products, quotients, and then we thought about functions of functions, where we used chain rule to differentiate. And then finally, we had a look briefly at how we use some of that, so why it's useful to think about maxima and minima. But we will come back to that in differential equations and through the course. Okay. Any questions at the moment on differentiation? Brilliant. We're going to dive straight into the sort of reverse integration. But I'll just swap my slides. I'm not sure how I've managed to do that. Hey, thank you. Brilliant. Okay. So, like how we were thinking about exponentials and logarithms, if we've got a function that takes us one way, we might be interested in a function that goes the other way. So we've been talking about differentiation, but we might also want to go the other way, in which case we're going to use integration. That's going to help us solve differential equations. So we're going to go through what it is, what we're actually doing, how we define it, and the geometric interpretation. We'll go through a few techniques. Integration has lots of techniques. They're not necessarily as fun, in my view. And then we'll go through some applications. So you can use it for area under curves. You can do cool things like designing very curvy like shapes, or and then thinking about the volume or the area inside them. But we're mostly going to use it for differential equations. So this should read integration, apologies. So integration, what are we doing with it? We're essentially reversing differentiation. If we had y is equal to x squared and we differentiated it to get dy by dx is equal to 2x, which we've just seen, our integration, which we write as this, so the integral of 2x with respect to x, so you need the dx, is x squared. So here we say that x squared is the indefinite integral of 2x. I'll come back to what I mean by indefinite or definite integrals. But essentially we're saying integrating 2x with respect to x, dx, is x squared. One thing to remember with this, and books will really emphasize it, and so will we, is that the integral of 2x dx is actually x squared plus c, some constant that we don't know. And the reason for that is, let's think about differentiating. Here we've got two functions added together. We know that we can differentiate them and just add their differentials together. If we differentiated x squared, 2x, that's fine. If we differentiate our constant, we get 0. So every time we integrate, we always have to account for there might be a constant, and it just disappeared in differentiation. So when we integrate, we actually get lots of solutions, because they might have this constant, which essentially moves the line up and down, or the whole function up and down. So we get information on the gradient, but not where it's sitting on the y-axis. So we might have something that looks a bit like this. So here we've got our differential equation, and dy by dx is equal to 2x. We know we can integrate that, and we get our x squared plus c, because the constant disappears in differentiation. So in terms of solution, all of these graphs are a solution to this equation. So we need an extra piece of information to figure out which one of these, or the infinitely many other ones that we could have on this graph, which one of these is the actual solution we're looking for. So when we solve our differential equations later on, we might have dy by dx is equal to 2x and another piece of information, something like, well, when x equals 0, y equals 3. That means that we could explicitly find which of these lines is the appropriate solution. Okay. So, I mentioned that we had an indefinite integral. We can also have definite integrals as well. And essentially all this comes down to is, when we write our integration sign, are we putting limits on it? If we aren't, then it's indefinite. We're looking at a general solution to our integration. If we put limits on it, we're essentially saying, what's the integral between point A and point B? We've now got limits on where we're looking. So, we've got an equation f of x, well, a function f of x. We're integrating that with respect to x to give us our general solution, capital F of x plus c, our constant of integration. Then we can write our definite integral as this. So the integral of little f dx is equal to capital F at B minus capital F at A. Okay. So rather than looking everywhere, a general form, we're putting limits on our integration. We're looking in a particular window. So if we had the integral of 2x dx between 1 and 2, we'd integrate this. We know it's going to be x squared. We've done it before. And then we put in our limits. So we've got 2 squared minus 1 squared is 3. That's our definite integral.
Sorry?
Yep.
Okay, all right. So when we were talking about differentiation, so I understood that we are looking at the gradient, how y was changing with respect to x. So when we are doing the integration, so what are we doing?
So it's almost like you're hiding part of the puzzle. So on differentiation, we had our equation that we were interested in, and then we're thinking about what does the gradient do? How is that changing as we move along our line? If you hide the original equation, you've just got that gradient changing. And that's where we might use integration. And again, we can only pull back, we can get a lot of the information back by integrating, but we don't know where it's sitting on the y-axis because we've only got information on how that gradient's changing, not where that line or that curve is on the y-axis.
So basically we are recovering information from how the gradient is changing.
Yeah. I think, so often it's nice to start with differentiation, but a lot of the time when we're putting together models, we're starting with this idea that we understand how, or we want to understand how one thing's changing with respect to another. So how are infections changing with respect to time? So we actually start with a differential equation. And then we integrate to get an idea of, okay, we want to know the number of infections at a point in time. We might integrate for that. So often you actually start with a differential equation rather than starting with the original equation. But it's nicer to, well, learn differentiation first and then look at integration as the reverse of it. Okay.
I was also seeing when you've added the limits a, b, it's like we have lost our constant c.
Yes. Yes. And you are very right to add that. This is also another shorthand. So what we're saying is, okay, we've got our f of x plus c. But really, this whole thing is the solution, our indefinite integral. So we've got plus c on both of these. So what we'd have here is f of b plus c minus f of a in brackets minus c. So the c's cancel, and we just skip that step in this. But you're quite right. There should be a constant on both of these. We're just assuming that they cancel them. Okay, so good to look at another brief example. So here we've got y is x cubed. Then the differential is 3x squared. That's all right. When we calculate the indefinite integral, we get our x cubed plus c again, constant of integration. And then if we're thinking about the definite integral, and I'll show on a graph what that looks like. We have our integral equation here. And then we've got our limits 0 and 2. So we integrate plus c. And we put our limits in there to get our value, our numeric value essentially, our definite integral. It's another notation thing, but it's worth mentioning. So here we've got our integration here. As we've seen, we've got x squared there. Essentially, it doesn't matter what we write here for x. As long as we preserve the function that we're trying to differentiate, we could write it as s or x. Doesn't really matter here, because as we integrate and we put in our limits for our definite integral, this variable drops out. If you were doing an indefinite integral, it wouldn't be the case. So, just a notation thing, really. Okay. Like with differentiation, there are a bunch of rules or kind of examples of integrals that people have previously worked out, And you don't necessarily have to work out from first principles, but it's useful to remember them, or use a program that remembers them for you. Here are a few examples. We've already seen if you integrate x to the n, you sort of have to, if you imagine the reverse, you'd have to divide by 1 of n plus 1, x to the n plus 1, plus c. We've got a few other things that you can sort of see from the reverse. If we've got y of x is equal to 1 over x, then the integral is log base e to the x, and so on. So we've got a few examples like this, thinking about fractions and how that's in log base e, exponentials, and then trigonometric functions. Again, if you've got a good feeling for these rules or these examples that someone else has already calculated, and then you've got an idea of how to put them together, so some rules for thinking about products, constant multiplication, then you can start integrating more complex overall functions. Again, if we're thinking about sums and differences or constant multiples, it's nice and straightforward. If we've got two functions added or subtracted, we can just do the integrations separately. That's fine. If we're multiplying by a constant, we can just take that outside the integral. That's also fine. So for those, it's quite straightforward. There are plenty more rules on this. They take a bit of time. We've got a couple of examples coming up later in the course. This is another thing that, as Andrew said, we could have a whole semester on it, and some of them take a long time to work through. You might have to apply different rules multiple times. So, if you get more and more complex functions, you might use integration by substitution, integration by parts, you might have reduction formulae. But it's very easy to start putting together functions where there's no closed form. And when we start putting models together, start with a very simple thing, I don't know, again, that mosquitoes are more active when it's warmer, a linear function, but then we know that mosquitoes don't like being too hot, so we need some sort of turning over. We might need to include some mortality. We might want to include how their biting rate changes and all of these things. As soon as you start adding in all of this and then want to integrate it, very quickly you arrive at something where there's no closed form. Again, it's helpful to see where these things come from, so you get a feel for where they come from and how they might be used in your work. So, I promised a graphical interpretation. If we're thinking about a definite integral, so again, we're integrating, but we're looking between limits. We're thinking about the window where we're integrating. What we're getting at, rather than thinking about how the tangent follows the line, we're getting the area under the curve at that point. So here is our differential that we worked out previously, and we're working backwards. So our limits on our definite integral are 1 and 2. We've got this equation here, and we can use integration to figure out what this area is. As you can imagine, let's say you wanted to 3D print a vase, and you wanted to fancy shape something that looks like a couple of quadratics added together, and then you wanted to figure out what the volume of that vase was. You can start doing that with integration, if you want to. So it's quite useful for figuring out the area under the curve. And with a definite integral, we've got the bounds given. We've got this equation really as our theorem for how we define a definite interval. And what we're always thinking about with definite integrals is the area of the curve in between these 2 points. And we should have a separate handout for you in terms of how you come about this equation. And again, rightly on your point, when we're thinking about a definite integral, those constants of integration essentially cancel out. So, we integrate to find the area under the curve. We've got bounds in the definite integral. We can use this to start getting an idea of, okay, what is the area under this curve? This is handy when you start thinking about probabilities. But for an example here, we've got an equation, y is 7 minus x squared. We've got quadratic. It's an unhappy one. We've got a y-intercept of 7. And we've got 2 roots. We might want to know the area under the curve for this section of it. And we can define our definite integral to get an idea of that. So we've got our bounds, -1 to 2. We integrate our quadratic. So we treat each of these separately, because we're just adding together functions. So we integrate. The constant of integration cancels out in a definite integral. And we put our values in to arrive at our area under the curve. Okay.
So what does it tell us?
Depends on what your equation is describing. So let's say you've got, going back to, let's say that 3D printing example. So I've defined a shape. I've told my 3D printer I want essentially kind of a semicircle type thing. I've defined this curve with this equation, and I've defined the back of my vase or the shape that I'm creating using kind of the x-axis essentially. I can use this to give me an idea of what the area is here. So maybe I need to know how much material to put into my 3D printer so that I can print this shape. If this had another Z direction, if you imagine it coming out of the screen, you could think about what's the volume of all of that as well, once I've 3D printed it. We'll also come back to that in probability as well. So you might be interested in, okay, we've got a probability distribution, and we want to know how much of essentially the probability lies within a particular region. So that's another example why we might use this. Okay.
Question.
Yeah.
Please correct me if I am wrong. So the way I'm trying to think about this differentiation and integration is this. So let's say we are trying to like model something now, and then we have our data, then we generate an equation, like a function. So we use differentiation to determine how our dependent variable is changing with respect to the independent variable, right? Okay, so if you now want to know what happens, or let's say want to predict, or want to go back in time, that what happened at this particular period, let's say between 2019 and 2020. So that is when integration comes into play, right?
That's a good one. Okay, so for me, I always have to put like an example or an application. So let's say our equation is describing a number of infections.
Okay.
What we get when we solve it is the number of infections on a particular day. And your question about what happened between 2018 and 2020, maybe we're looking at, okay, the total number of infections over that time period. So that would be giving us, well, that would be a result of us integrating our equation.
Okay,
we're
but
getting
if we're to predict, let's say want to go ahead now, want to forecast. So,
okay, forecasting is a slightly different, yeah.
So, but will integration also work in that regards?
So just coming back to the forecasting point, so let's say you've defined your model, you've related it to data, you've fit it or estimated to data. You do that using data that's already happened in the past. So maybe you're thinking, okay, well, the thing that my model really needs to capture is the number of infections between 2018 and 2020, and I need to make sure that my model reflects that. So let's say you've got values of your coefficients or your parameters in your models so that it matches up well with what the data is saying between 2018 and 2020. Then you've got an equation or a model that you can use to project what could happen in 2025. So it's your equation essentially is the same for both of those time periods. You estimate it on past data, you project into the future, but your equation stays the same. And as I mentioned, when we start thinking about these things, we're often starting at the point where we want to relate the dependent variable to the independent variable. So we want to relate number of infections to time. And we might be saying, well, infections are increasing with time. That's a linear equation. We've defined our first model. It might be rubbish, but it's a starting point that we can then build complexity. So we almost start with the differential equation, and then to solve it, to get an idea of the number of infections on a day in the past, or thinking about projecting forward, then we use integration. Okay.
Thank you.
Okay. Right. So we've gone through some examples and thinking about, okay, we've got an exponential function here, we're going to integrate it. So this is our indefinite integral in the center of those square brackets. And then we put bounds on it, and we got our definite integral. We've got a dummy variable s, it's just notation. But we put our bounds in, we substitute them for our value of s to arrive at our solution to our definite integral. So what's this saying? Well, this is, our blue line is e to the minus 3s, or x. We're going between s is 0 and s equals 0.5. So we've got a well-defined window where we're looking at our integral. We're looking at the area under the curve in this place. We could also say, well, I've got a curve and I want to know how much area is under the entire thing. So in that case, we might write it like this. So it's essentially all the same. We're going from s equals 0, but our upper value is x. So it's some place along this axis, but we haven't defined it yet. So essentially, we can move this like a slider. Okay. So we do our indefinite integral inside the square brackets again. We've got our range, but now our range goes up to x. Unfortunately, x looks like a multiplication sign, but same principle. So we've got our bounds, we put them into our indefinite integral, and we've got what looks like a definite integral, but we've got this x. That's our slider along this axis. This is useful because then we can start asking slightly weirder questions like, well, what's the area under this entire curve if we look towards infinity? We'd call this an improper integral because we don't have like a real window. We're looking from one side of the window all the way out to infinity on the other side. We work it out like we just did, so having x as our upper bound. And then we take the limit as x tends to infinity. And that defines our improper integral. What do we mean? Well, we do the same thing that we did before, but we take this limit as x tends to infinity, so as x gets really large, what is our function going to look like? If we do this, well, we've got x only appearing here, e to the minus 3x. E to the minus 3 times something massive becomes very close to 0. So it tends towards 0 as x tends towards infinity. So quite nicely, this part disappears. And what we get for our improper integral of e to the minus 3s is that the area under the curve is a third. Again, it's weird. We've got a window where it's got a clear edge on one side, and then we're looking out to infinity on the other side. But if we kept going to infinity as if it was a place, we'd end up with this area under the curve of being a third. Again, this is also quite useful when you start thinking about probabilities. Okay. So, applications we've seen, we can find areas, and we can be thinking about a definite integral to give us the area of a thing. Again, thinking about that 3D printing example. We also use it for solving differential equations, and we've already done this a bit so far. This is what we're going to do a lot of, but we've got a whole lecture to talk about differential equations. And I think we're coming up to speed networking time, if not eating into it. So, just to summarize, within integration, we've talked about it being the reverse of differentiation, but often you're starting at your differential. We've looked at a bit of what it looks like on a graph and geometric interpretation, and then we talked about definite and indefinite integrals. What's the difference? And then we've gone through a few rules. Again, you'll get the slides, so you don't have to memorize them. And how you play with those rules, how you add together functions and integrate them. And then finally, a little bit on applications. But as I said, this is something that we're going to be focusing on in the differential equation lecture and then throughout the course. Okay. Any questions on integration before we jump into speed networking? Brilliant. Time for a change from maths, I'm guessing.
Starting basic people who've done some basic maths. Just to zoom out again, detail, thinking of how and when we use these as tools. Okay. So if we want to add something up, it's like going back from, so if you've got rates, integration takes you to the original trajectory.
Right.
So like if we had a path of an aeroplane,
Mhm.
yeah,
Yeah.
and to differentiate it, we'd work out how fast the aeroplane's going.
Yeah.
Differentiated again, we'd work out how fast it's accelerating or decelerating. If we integrate the rates, we then get back the original curve, the original trajectory.
Right. So earlier, what she was making the lecture, she was saying it gives you the area under the curve, then it gives you the total number of diseases or cases in a period of time. Then would it be possible to say at a specific point in time, the starting time, what is the incidence like, instead of having prevalence over a period of time, for example?
So yes, converting between incidence and prevalence.
So for example, let's say December 2019, let's say we have maybe 5-10 cases of COVID in the world, for example, or maybe in a specific area, for example, and then fast forward 2021 December, you could actually integrate back to maybe December 2019 to say, okay, these are the number of cases we expect within this period of time. But then, would you be able to predict to say in December 2019, specifically that particular month, without having to consider January, February, March of 2020 to 2021, how many cases are there just in December? Just saying, okay, would you be able to predict that first 10 cases, for example?
So if you know the prevalence over time, you can differentiate it to get the incidence, because incidence is the rate of new cases per time, okay? And you're absolutely right. If you know the incidence, you can project forward by integrating. Now that's what we call extrapolating. So if we assume that that rate of incidence is constant, we can extrapolate forward, okay?
Right, yeah.
Now in the same way as that cartoon, that joke I had about the number of people you're married to, if you extrapolate, that will just increase without limit. If you do that with infectious disease rates, you have the same problem. You're going to be overestimating to what extent, to what the incidence will be in the future if you do that, just based on the rate at the current time. So there's a very famous, notorious paper on looking at smallpox outbreaks, I think, which basically suggested the whole world would get infected within 2 weeks or a month, yeah? Because what it doesn't take into account is that your rate gets slower as you run out of susceptibles, okay? Which is the entire point. We need epidemic models, which is a different lecture.
Right.
Okay.
Thank you.
Super. Yeah.
Okay, so I want to understand how this relates to diseases. So how I understood this was when we are differentiating, of course, we are looking at the slope at different points. So there's a relationship, and then there's the gradient, which is when we differentiate that relationship, we get the gradient. So I'm looking at the integration as now we have the gradient. What relationship existed? Is that it?
So,
within a certain period?
okay, Katie's going to get into this in the next lecture, but where integration and differentiation are essential is they give us our link between mechanisms, which are typically expressed in terms of rates. So either the rate that people meet each other, or the rate at which you recover from a disease, or the rate at which disease ultimately is transmitted. These are all rates which we can measure. If we integrate those rates within a model, we can predict what the actual change in the numbers that are susceptible and infected are over time. Okay? Does that make sense?
Maybe.
Yeah?
I'm sure as we go. Yes.
So predict is very different from forecast.
Okay.
Okay? So a prediction, a model can make a prediction without any form of data. Okay? So we say there's some rate of transmission, there's some rate of recovery. This is what we would expect. So it's exactly like the hair links example. So if we've got a predation rate, if we've got a birth rate, a death rate, this is what we would expect. We'd expect to see these types of cycles, this sort of epidemic curve. Okay? That's a prediction. Okay? And that's completely different from a forecast, which would be saying, this has happened, we expect this to happen next.
Okay.
Yeah? Where they come together is where you fit your model to past observations. You then make predictions which are also forecasts. Okay? So you don't need a mechanistic model to make forecasts. So you can make forecasts with a statistical model, with a machine learning model. It just might be very wrong, depending on what data has gone into it. A mechanistic model knows something about what happens when disease spreads, and that gives you a better prediction, or a better basis for prediction.
I'd also add to that you've got another thing, which is projecting.
Yes.
So often we'll use the term projecting because a prediction does sort of imply that you think that's what's going to happen. But the reason to use projecting is that captures that you've had to make certain assumptions in what you're doing, and you're making certain assumptions about the future. So if we think about vaccination, or what we think the burden of disease is going to be in the future, when we're looking towards the future, we might have had to make certain assumptions about, okay, what's the routine coverage achieved next year? Are we expecting any campaigns for this particular disease? Given that there was an outbreak, or we were expecting an outbreak response campaign in terms of vaccination. When you're modelling 5 years into the future, you've had to incorporate some sort of assumptions or some scenarios around future vaccination. So your projection is based on those assumptions. And it might be that that's what you're interested in, right? You might be looking at different vaccination scenarios. What happens if I vaccinate 80% of my population, 70%? What's that going to translate to in future burden? So the projections for each of those different scenarios are essentially using your model to say, this is what we think might happen given this scenario and given how our model is fitted to previous data.
So these distinctions are important, and I think it was interesting as someone who wasn't actively involved in doing COVID modelling to see how the modellers who were involved in COVID modelling rapidly moved away from using terms like prediction,
yes,
which have a very specific mathematical meaning, which is fine, and they started using projection.
yes.
And for me, I think the problem with prediction is it implies that you actually know what's going to happen. It's that crystal gazing thing. And forecasting's even worse, because
Yeah.
you're actually saying this is going to happen, it is going to rain tomorrow, and people get upset when it doesn't. Projection is a better word, because it captures that idea that we're saying, based on this model, which is wrong, this is what we think will happen. Yeah? Yeah? Which, you know, the language we choose is important for interpreting what it is we're doing. So because that evidence projection is still useful for a policymaker. Yeah? They need to know, based on what we know, this is what we think is happening. That's useful to know. And it's useful to know that that's different from this is definitely going to happen. Yeah.
Based on what based on what we've discussed so far, will you just give me a very simplistic definition between the difference between statistical modeling and mathematical modeling?
Okay.
I mean, this question comes up a lot in interviews, and people have a different way of answering it, but it always seems to come up.
You're going to cause a fight between me and TJ, and he's not even here yet. So
We'll tell him what happened.
for me, and that's because where do I come from? I was a physicist in my training, and we don't really worry about stats very much as statistical models, because we just do as many observations as we need to get the answer, so that the stats doesn't matter. So from a physicist's perspective, the difference is statistics is essentially phenomenological. It's building a model to describe, as I presented it, variations in data, and to understand that variation in data without having a mechanistic basis necessarily for what's generating the process. Now, that's a simplification though, because there's statistical models which are based on mechanisms. So nuclear decay is a really good one, so there's a constant rate. You know, there's a physical law there which generates a statistical distribution which we can test empirically. Okay, so the lines are blurred between statistical modeling and mechanistic modeling, and sometimes mechanistic modelers will maybe be a bit disparaging if it's just a statistical approach. Well, what they mean is it's just an extrapolative approach. It's just a non-mechanistic approach. You can, and in fact TJ will be talking about it at the end of the course, you can treat mechanistic dynamic models as statistical models, and you can estimate them in a robust way. It's just really, really hard. Yeah, but you can do it. There's no reason you can't do it. The distinction ultimately comes down to whether or not you have any data. Yeah? If you have got data involved at all and you are using that data to infer the values of parameters, you are doing statistical modeling. Okay? So almost everything that I do in terms of modeling is statistical modeling, but I wouldn't consider myself a statistician. Yeah? But a lot of modelers would consider me a statistician, because why are you mucking about with data so much? You know, I spend most of my time dealing with those issues. So it's a subjective thing, and that is something where it's a common thing that I think will come up in a lot of points of the course, where, you know, we're going to teach you the techniques, the sort of basic technical skills you need to do this, but modelling is also an art, because there are a lot of decisions, judicious decisions, about what assumptions you make, why you make them, how you justify them to people, which feed through into everything that you've done. And different people will make different assumptions, which is why one model is never enough. We need lots of models, and we need a transparent discussion about how those models work and what they do for modelling to be useful. Okay. I don't think we've got enough time to do speed networking.
We could just say...
I have a feeling we should maybe just go through the room and get everyone to introduce themselves. And then at least we've all got each other's name. We've got a starting point for conversations over lunch and at breaks. The reason we did the speed networking before is because we always get tempted to talk for too long, and I'm doing it right now. I'm talking for too long, but we should just get on with it. Yeah. So we are going to do a timer, and we are going to do 2 minutes. Have we got enough time for 2 minutes? We're going to do 1 minute for everyone. We're going to go around the room, 1 minute. We want to know who you are. We want to know where you came from. And we want to know why you're here. Okay? 3 points. And we will start with you.
Okay. All right, so good morning, good afternoon. Don't know what time it is.
1 minute.
Okay, all right, good. So my name is Roland Christensen Ameto. I'm from Benin, and I'm a PhD student from the Mahmoud Consortium, and I'm a PhD student as well from the African Institute for Mathematical Sciences and the Swiss Tropical and Public Health Institute. So basically what I'm doing is I'm looking at the impact of malaria interventions in Benin, since we are trying to eliminate Benin. So first, I'll be looking at what happened in the past, so the retrospective impact analysis. Then what will be happening in the future. Then I'll be looking at the validation of the parameterization of some intervention in an agent-based model. Basically, I'll be using open malaria. And lastly, I'll be looking at cost effectiveness analysis. Thank you.
Okay.
So my name is Gloria Ejewabuchi. I'm from Ghana, University of Ghana. I'm with the Department of Mathematics. I'm a lecturer there. I'm into disease modeling a little bit, not too much. So more of compartmental deterministic models. But I realize there's a gap between the public health professionals and the mathematicians. So I want to link that gap, know what goes on with public health. Like I'm saying, I understand the math bit, but I can't interpret the public health side of it. So I want to understand what goes on with that and the interpretation of some of the things we do in disease modeling. Yeah.
Okay, my name is Nana Abateto Aisen. I'm from Ghana. I work as a project coordinator with the West African Mathematical Modeling Capacity Development in Ghana, but it's based under the Department of Medical Microbiology. So I also work on a project, epidemiology of complicated malaria within children from 0 to 15 years in some selected hospitals. So I'm here to learn much of Bayesian methods and mathematical modeling so that I can use it on this project. Thank you.
Okay, I'm Dr. Mubolaji from Nigeria. I had my background in agricultural economics, but my PhD study focused on effect of maternal health care utilization on child immunization and mother's well-being in agricultural settings in Nigeria. So I'm basically here to improve my understanding on health economics so that I can further project my research on how to better improve the life and well-being of mothers, especially those in low resource settings. Thank you.
Hi everyone, my name is Millicent Makandi from Kenya. Karibuni sana. I work at the Ministry of Health at the Unit of Integrated Disease Surveillance, and I'm here to learn on how we can use mathematical modeling to better improve our disease surveillance and response. Thank you.
Hello, everyone. I'm called Pamela Bakablindi. I'm a medical doctor and immunization specialist with the World Health Organization. So I'm more at a policy level. I've been working with the yellow fever team in Geneva, and we're trying to put modeling into yellow fever. I've been running immunity gap analysis for the African countries that are high risk. So I'm basically here to learn more about how these models, how we can use these models for decision making. Yeah.
Okay. Good afternoon, everyone. My name is Suleiman Idris, and I'm a PhD student in public health. I'm actually also an epidemiologist. I've worked on vaccine-preventable diseases, and I've also planned and executed immunization, mostly for polio and COVID-19. So my project right now is focused on mortality surveillance for Lassa fever and dengue in Sokoto State, Nigeria. I came to this program because I wanted to learn a lot about modeling and how to apply that to the immunization sector. Thank you very much.
Hi, nice to meet you all. My name is Abdurrahman Ahmed. I'm from Somalia. I work at Somalia National Institute of Health, which is part of Ministry of Health. I hope to gain here insights on various models using vaccine-preventable diseases, which I hope to apply in our local context. Thank you.
So good afternoon, everyone. So my name is Adeni Abib from Nigeria. So I'm a microbiologist by profession, but now, so I'll say I'm a data scientist by condition. So basically, so I work for the Global Health Research Global Resistance. So we have like collaborators in the UK, we have collaborators also in the Philippines, and we also work hand in hand with Nigerian CDC. So basically, I'm just here to learn about how we can use modeling to make decisions in Nigeria.
Hello, everyone. My name is Bright Adoble. I'm from Ghana, and I recently completed my MSc in vaccine production quality control, and also I was a research assistant at the Pan-African Vaccine Center, and I'm hoping to do my PhD in future around health security, and I'm here to learn more about modeling with relation to understanding the public health impact of vaccination. So, yeah, thank you.
Hello, my name is Serigne Diagne. I'm from Senegal, and I'm PhD at Institut Pasteur of Dakar, and I am in the AMAX project, and I work on and my topic is to develop a mathematical model for the PSPV in Senegal, and I make decision. Sorry, my English is very bad because I come from Senegal. We speak French. Thank you.
Good afternoon, everyone. My name is Jacob Kazungu. I am a postdoc at Cambridge Wellcome Trust Research Program, and I'm here to learn more about modeling. So we have a project where we want to enhance the use of economic evidence in vaccine policy making in Africa. So we are doing that in Kenya, Zambia, and Nigeria. Don't know where that echo is coming from. Yeah, so I'm here to learn, and I'm looking forward to meeting people from across the continent.
Good afternoon. My name is Prashant Mandalia. I'm originally a pharmacist by training, but also a health economist working at Cambridge Wellcome Trust. Also working on the same project on use of vaccines and decision making using economic evidence. So yeah, I'd like to learn more about modeling of vaccines, mathematical modeling. And yeah, meeting everyone here and networking later on. Thank you.
Hello everyone. My name is Kemunto Ogutu. I work for SEMA as the Health Communications Intern, and I look forward to interacting with a lot of you as I do my work today. Thank you.
My name is John Ojal. I mostly focused on assessing value for money for vaccines, and I use modeling and health economics in that particular process. I work at the Kenya Medical Research Institute at the Kilifi campus, and I'm here to facilitate some of your practical sessions with Andrew.
Good afternoon, everyone. My name is Mercy Chepto from the Ministry of Health, also working with my colleague at the Division of Disease Surveillance and Response. I'm a medical microbiologist and an epidemiologist as well. And I am here to learn more on modeling and how we can use this technique to determine disease outbreak progressions and inform policies.
Good afternoon. My name is Fred Monari. I'm a lecturer by profession from Kisii University here in Kenya. And I have a background in applied statistics. But my main interest in this, since I know a bit of modeling, I want to have a bias towards the medical part of it, especially the public health. So far, I normally teach these public health courses, especially about statistics, but there are some element or some aspects of it. Like for example, if you say that smoking and lung cancer are correlated, yeah, we want to find the correlation between the same. We need the smoking because we are going to use the same like observational data. So there are some confounding variables which normally affect, which are not the part of it. So that's what I'm eager to learn here, because if we say smoking causes lung cancer, we have the data on smokers and the data on lung cancer. But there are some variables like age, like what on those not, like exercise, lack of exercise, all those are confounding variables, and that's what I'm interested in this training. Thank you.
Good afternoon, everyone. My name is Alain Balolan Taboba. I am from Bukavu, DRC Congo. I am a medical doctor in internal medicine at the Referral and General Hospital of Bukavu. I also work as a fellow researcher at the Center for Tropical Disease and Global Health of the University Catholic of Bukavu. I am here, I hope to get more skills to get modeling skills in order to contribute to the development of my center. I am not so strong in English. I mostly speak French or Swahili, but I try. I am very only in writing English, but not speaking. Thank you.
Hello everyone, so my name is Oge Akabuike. I'm from Nigerian Center for Disease Control and Prevention. I'm a molecular lab scientist and environmental health consultant. So I'm here to learn A to Z of mathematical modeling. This is actually the first time I'm being exposed to it, and I hope to apply lessons learned to what we do in NCDC. Thank you.
Hello, my name is Aminu Mohammed. I'm a medical doctor by background, and I trained statistical epidemiologist. I specialize in immunization generally, with more expertise in global health generally, as a fellow from Harvard University. I currently am working with Task Force for Global Health as the regional advisor for their vaccines programs in West and East Africa, and also doubling as a country lead for the pandemic preparedness and response support in Nigeria, supporting my colleague here at the Nigeria Center for Disease Control and Prevention. My work really also just is more around the policy level, strategy, designing project implementation, and how to operationalize it. A little bit oscillating from the top to the middle area now. I've been at the lowest level too. So the reason why I'm here in this program is because I just concluded the advanced course on vaccinology, and there was a touch on vaccine impact. So I felt this is a great opportunity to learn how to apply this skill set into policy translated across the region. Thank you.
Hi everyone. Hi everyone. My name is Gladys Yamanda. I am a monitoring and evaluation officer at Washington State University Global Health Kenya. Karibuni sana. My background is or was in pure and applied mathematics. So I have really thoroughly enjoyed the session, and I can't wait for the rest of the week. Yeah, it's more of a refresher course, but my motivation is to re-engage with
everyone. Good afternoon. My name is Cosmas Biwot. I work for SEM as a statistician, and it is right time that I've enjoyed the course, which I think also will also equip my skills again. I have a background in applied statistics and also biometry, which is a biostatistics. Thank you.
Good afternoon. I'm Brian Ogoti. I'm a virologist, just submitting my PhD last year. I work in SEMA. So two objectives. One is I'm happy to see a couple of microbiologists, medical lab scientists. So the idea is to try bridge the gap between what modeling does and what we hide in the lab to do. So that's the first objective. The second is try to understand how we can implement this, especially in the vaccine-preventable infectious diseases, how we can integrate modeling and just having a refresher. And also the last objective, I don't know if this is possible, is what you talked about, experimental data. We generate lots of that. How do they play a role in this kind of modeling? Yeah. Thank you very much.
Yes, good afternoon, everyone. Ronald Chiemba is my name. I am a medical doctor. I also have an MSc in clinical trials from University of London. I work as a research scientist at the Medical Research Council, or Uganda Virus Research Institute in Entebbe, where we are working on a vaccine for schistosomiasis under the controlled human infection model. So I'm basically here. I want to learn a few things about mathematical modeling. So if I come across a paper, or if I come across a work of a modeler, I am able to critically appraise and rather rubbish or make sense out of whatever model has been, proposed. Thank you.
Hello, everyone. I'm Latif. I'm from Malawi, so I don't speak French. I envy those who you do. I'm also a medical doctor, a master's in vaccinology and also a master's in epidemiology. So I sort of wear two hats in Malawi. At MOW, I work as a vaccine researcher, so I'm involved on the right side of the vaccine life cycle, so vaccine evaluations, malaria, COVID, cholera, so forth. I'm also a PhD student at the University of Liverpool, looking at improving methods of vaccine impact evaluations to separate those from concurrent public health interventions that also affect the same disease. Thank you.
Good afternoon.
I'm Maslin Ganda, a molecular biologist by profession and a data scientist by passion. Back home at the Scientific and Industrial Research and Development Center, we are into the development of vaccines. So I'm here to acquire knowledge about mathematical modeling because I believe that it will play a pivotal role, especially when we go to our clinical trials. In addition to that, I also have a task to develop a mathematical model on the comparative effectiveness of foot and mouth disease control strategies that are being employed back home. So I can't wait to tick the done box, courtesy of SEMA. Thank you.
I'm Zoni Dembo from Malawi. My background is in public health. I've been working providing technical support to the Ministry of Health, the immunization program, on routine immunization as well as surveillance for vaccine-preventable diseases. But I have very minimal understanding of how to apply mathematical modeling in evaluating the impact of vaccines and also in applying it in public health setting. Thank you.
Good afternoon, everyone. My name is Wongai Mildred Pepukai, but you can just call me Mildred. And I am a biostatistician by training and an upcoming infectious disease modeler. So I come from the Biomedical Research and Training Institute in Zimbabwe, where I am the biostatistician on site. And I'm also a PhD student at the University of KwaZulu-Natal, PhD in statistics, majoring in infectious disease model, where I am trying to develop an age-structured stochastic tuberculosis model with applications of machine learning, evaluating scenarios of what will happen when we introduce an adult vaccine candidate. Currently, tuberculosis is vaccinated at birth using BCG. So what will happen when we have BCG and an adult vaccine candidate? So I'm anticipating what the vaccinologists are doing as they are developing vaccines. So I'm in place to be able to model the impact of what happens in our populations. Sorry. I think my 1 minute is up. Yeah, so I'm looking forward to networking more with everybody. Thank you.
Good afternoon. My name is Robina Naranga. I work with the Medical Research Council in Uganda. I'm a biostatistician by training, but I'm also a PhD student at London School of Hygiene and Tropical Medicine. So my work is looking at how to improve the overall benefits from vaccination. So I want to develop a framework which evaluates the different strategies that evaluate how someone can really fully benefit from vaccination. So I'm looking at incorporating the immune response, but then also the coverage for a vaccination program. Yeah, so I'm here basically to learn our programming skills and how I can apply this in my current PhD, but also I have an interest in economic evaluation using models.
You will get your workshop to work. Okay, my name is Jetnet Gedef. I am from Ethiopia. I work on university lecturer and research. I'm public health in health system and policy, and I got a short course on vaccine strategy and for vaccine preventable disease. So I'm highly interested to this training. Thank you.
Okay, thank you. Good afternoon. My name is Mizana Tamikail. I also came from Ethiopia. I work at the Addis University under a research project called Addis Center for Ethics and Priority Setting. We mainly do costing exercises, costing and cost effectiveness studies for different health interventions. So I am also doing a second master's in public health data science, and I am here to know more about how mathematical modeling can be applied in the public health side and how it can better assist decision makings. So thank you.
Good afternoon, everyone. I'm Paulina Kalimbo. I'm from Namibia. I'm a lecturer and a researcher at a private institute in Namibia, Vaccine University. By my background is I have a master's in public health from the University of Nairobi. Proud to be back home here. So why am I here? I want to pursue my PhD with a focus on infectious diseases modeling and evaluation of public health interventions. So I believe this will be will provide me with the strong vital skills for that. Also to network, you never know. Yeah, thank you.
So afternoon everyone, my name is Ivan Sonyango. I am from Kenya. I am a medical doctor by profession with a master's, or should I call it a specialty in internal medicine. And so when you look at the title, everything here is sort of familiar to me, vaccine-preventable diseases, apart from the first bit, mathematical modeling. So that is quite foreign to me. Like my colleague, it's the first time I'm being exposed to it. And I don't think many internal medicine specialists are into modeling or even research at all. And unlike my colleague Gladys, who's can't wait for the complex mathematical equation, I hope it will be simplified for some of us. Thank you. Oh, sorry, I work at SEMA as a research physician in some clinical trials, mostly HIV. Thanks.
Hi everyone, I'm Richard Japi. I'm from Côte d'Ivoire. Côte d'Ivoire is not Côte d'Ivoire. Côte d'Ivoire is the country that won the last AFCOM in February. Yeah. I'm an epidemiologist by training. I was first introduced to modeling when I was doing my PhD at Swiss Tropical and Public Health Institute in malaria and helminth co-infection to predict the prevalence of the disease in the entire country in Côte d'Ivoire. After I shift to zoonotic disease like brucellosis, and now I'm working with a meningitis group, which is part of the VMC, and here we would like to apply mathematical modeling to see the impacts, how climate parameters can predict meningitis outbreak, and how vaccine can help to control the disease. Thank you.
Thank you very much. I'm Isaac Fwemba from the University of Zambia, School of Medicine for now. I wear a hat of a statistician with keen interest in Bayesian method. I can't wait to have the other colleagues speak the Bayesian language. I'm particularly interested to see how really the various Bayesian approaches that we have, both from the deterministic approach using the nested Laplace approximation, as well as probably the hybrid using the STEN now, and maybe using the quite computational cost method, the sampling-based approach can be integrated and used in the framework of mathematical modeling. We are used more on the stochastic side, and it will be interesting to see how we can use this to evaluate a number of health interventions. Thank you.
Good afternoon. My name is Ruth. I have a background in pharmacy and a master's in tropical and infectious diseases. Where I work with Ministry of Health, mainly in the public health space, where I'm involved in mostly what we do is disease surveillance and response, and also supplementary immunization activities for vaccine-preventable diseases. where I am in my life right now, I'm aggressively looking for either a fellowship or a PhD opportunity that is going to look at either mathematical models or clinical trials in tropical infectious diseases. Why mathematical models? I believe they are invaluable tool for analysis of data, building simulations, and making predictions. This training, one, is an answered prayer, and two, it's a stepping stone towards achieving my career goals. So you mentioned of a fellowship. If possible, I'll talk to you later on and see how to go about it.
Good afternoon, everybody. My name is Jeanette Dawa. I'm the scientific manager here at SEMA. I'm facilitating one of the sessions later on in the week. Aside from that, my role here is to make sure that everybody gets what they needed from this course. And I can immediately see that we need to have some support groups. The support group that struggled in the morning and didn't really understand what was going on. The support group that can read English but speaks French. So we'll make sure that you get to interact and get the support you need so that by the end of the 6 weeks, you are happy that you came. 6 weeks? Oh, 6 days, 6 days.
All right, my name is Tumbi Mwangi, and at the end of 6 weeks, I hope to still continue talking. I work at SEMA. My interests mainly is in science of elimination, so mathematical models play a part for diseases that are either in humans or in animals. My first training was in veterinary medicine. And my real wish actually for this course is to have more of you take up modeling even post this course. And I think that's something that SEMA is interested in fostering for the continent, that there are more and more modelers, because the decisions that we make require more than we can hold in our heads through mental models. And I think maths models can really help with that. So hope you enjoy these 6 days, or 6 weeks.
I'm the last one, and between you and lunch, so I'll be quick. My name is Mutono Nyamai. I work here at SEMA, at the University of Nairobi, and I use mathematical modeling to try and give the government optimal ways of controlling neglected tropical diseases. That's things like schistosomiasis, someone mentioned that, and also soil-transmitted helminths. And I will also be part of the people assisting with practicals. So if you have any questions around the course or just about Nairobi, please feel free to reach out. And hope to interact with all of you during the 6 days and pushing it all along to 6 weeks. Thank you.
Of course, I was one of the ones that had the pleasure of selecting you for this course. And actually, I should have said this at the beginning. I don't know if it was shared with you. There were about 400 applications to come on this course that we had to screen. What? Oh, okay. Oh, over 500. Katie got rid of 100 for me. Yeah, over 500. And we could easily have given places to half, I think. It was incredibly difficult choosing the people to come on this course. As you will have heard, you all come from a very different range of backgrounds, geographically representative of Africa, we hope, as well as we could. You also have different technical abilities, and you're all chosen because you're really interesting and you've got really interesting applications. And we hope you all get different things out of the course. Okay, this course is, as I said at the beginning, designed for people who have no background in maths to get them doing modelling. So we're going to be mostly focusing on that hands-on stuff, but there's also going to be the invited seminars giving case studies, and we'll be talking about case studies as we go along as well. So what I want to emphasise is this subject is not a mathematician subject, it's a multidisciplinary subject. You know, you can't do it as a single discipline person, yeah? You either have to go native, like me and Katie, and learn all the biology, or you have to learn the maths. And it's only by talking to each other and working out where we can help each other, that ultimately we can answer these really difficult questions about policy. And I hope that's what we're going to learn together over the course. So thank you again, and look forward to getting to know you better over the course. Let's go for lunch.
So for lunch, we are going to the Norfolk Hotel, which is just next to where you're staying, at the Lenana, next to the Lenana Suites, and it's just down like a 5-minute walk, and hope to be back by 2. You can leave your stuff here. It's very safe.